Today we'd like to apply what we learned about entropy to engines. So we were looking at this idea of how many different microscopic states could we get with a given number of items. So in this case, we have 7 possible tiles for our Scrabble game. These letters are already determined, but we can swap them around in terms of the order of where we want to place them. How many different ways can this occur? We saw that there were 7, 6, 5, 4, 3, 2, 1, which worked out to be 7 factorial, or 5,040 different microscopic ways of arranging these tiles. We could put 7 different things in the first spot. Then once we establish our first letter, we have 6 different places where 6 different tiles we can put in the second spot, and so on. So it looks like with 7 tiles, we are going to have 5,040 different possible ways of combining them. However, realize that sometimes you'll get tiles that are interchangeable. So in this case, we have 6 O's. It doesn't matter if this tile is here or here, it's still an O. So these tiles are interchangeable. So instead of having 7 factorial, we only actually have 7 different ways of arranging these letters. Okay, we could have C in this position, this position, this position, or so on. But once you place your C, we know all the other tiles are O's. It doesn't matter which O goes where, because all of the O's are interchangeable. If they were all O's, we would only have one option, one microscopic way of arranging these, because no matter where the tiles were, it's an identical setup. Microscopically, it's got only one option. We saw that when we found the entropy, when we take the entropy of 1, when we take the log of 1, we get an entropy of 0. So anytime there's only one microscopic state that can describe what's happening, that is known as an entropy of 0. Okay, so let's apply this now to our box of gas molecules. So we got a box of gas molecules that are moving around randomly at different speeds, and we want to kind of know how many microscopic ways can we arrange them. Now, we're not going to get an exact number. We're not going to get a number at all. We just want to look at how is that number of microscopic states going to be different if the gas is hot versus if the gas is cold. And the key here is to think of these like the Scrabble tiles. Okay, when we have a cold system, it means we have lots of duplicates. There are a lot of molecules that are going to have the same speed as other molecules. And because of that, they're interchangeable. So even though we might have the same number of total particles in the box, whether it's hot or cold, we're going to get much fewer microscopic ways of arranging the speeds when it's cold. So what that means is when it's cold, our entropy is going to be a lower number than when it's hot. When it's hot, our entropy is going to be higher, because we're going to have more possible microscopic states. There will be less interchangeable molecules inside the box. Okay, the next thing we want to look at is an extremely important idea, and that is, what if we have a box full of molecules and they're all moving around, and we either add heat or remove heat from the box? In this case, we're going to add heat. So we're going to raise the temperature of the environment. When we raise the temperature of the environment, heat is going to go into the box and make the particles start moving faster. And we can see what happens to our graph when we do that. We can see that we get a greater spread of speeds. A greater spread of speeds, we saw, that means less interchangeable speeds, which means we're going to have a higher entropy. To calculate the change in entropy, we're going to use this equation. delta S equals Q over P. We take the amount of heat that went into the box, we divide by the temperature where that heat went into the box, and that will give us our change in entropy. Realize this assumes that the temperature is constant, okay, or near constant when we're doing this. So if we were actually going to do this for what you just saw, we'd have to use calculus. We'd have to figure out how much heat went in at each of the different temperatures and add them together. You are never going to have to worry about that at this level. So when we do this for all of our problems, we're going to assume that all the heat went in at the same temperature. Here we're going to remove heat from the box. This time we're cooling down the environment and heat is leaving the box. We can see that we're getting a fewer number of duplicate speeds, which is going to make the entropy drop. So when we do our math this time, our Q is going to be a negative number, and that's going to give us a delta S that is negative. A delta S that's negative may seem like it contradicts the second law of thermodynamics. The second law of thermodynamics we talked about meant that the entropy of a closed system always has to go up or stay the same. It cannot drop. The reason why we're able to get the entropy to drop is because we don't have a closed system. We're focused strictly on just one little box of molecules, and that system is not closed because heat got out of it. If we looked at how much heat went into the surroundings, we would see that the change in the entropy of the surroundings is going to be bigger than or equal to the entropy lost by the gas. So that the net entropy change will still either be 0 or a positive number. So bottom line is you can have a negative change in entropy so long as you are only looking at one part of the universe and some other part of the universe had a positive change in entropy. Okay, I'd also like you guys to watch this. Okay, we have this person on a pendulum, and we want to talk about in terms of energy and entropy.
Bob, this is not a good idea. Don't do that.
Nah, dude, it's fine. I'm on escape mode.
Okay, and we can see that we had a change in energy. We started out with potential energy gravity. We turned it into kinetic energy. And so long as we restrict ourselves to before the collision, we can see that we did not lose energy. It just turned from one type into another. And it also turns out that the entropy change is also 0. In fact, we could say the entropy of the object as a whole was 0 the entire time. Again, we're not going to think of it as individual gas molecules, but we're going to think of it as one big object. And if we look, every single part of the object is going to be moving at exactly the same speed. So it's kind of like having our Scrabble tiles with all zeros, or all any letter. Okay, there is only one microscopic state where every single part of the object is moving in the same direction. Okay, so this big object, no change in energy, no change in entropy. Finally, we'd like to look at the heat flow. So we're going to have a hot and cold container of gas, and we're going to put them in contact with each other. We'll assume all of the heat transfer happens from one object to the other, and we are going to have 1 kilojoule of heat move from one container to the other. We're going to assume that that is not enough heat to significantly change the temperature of our two environments. And what we do is we find the change in entropy at the top. The top loses 1,000 joules. The temperature at which it lost those joules was 350. When we find the change in entropy at the bottom, it's going to gain 1,000 joules, and its temperature is 300. So we work this out. We're going to get a negative entropy, we're going to get a positive entropy, and we're going to see that this is bigger than this. So the delta S of the universe when we combine both parts of our system, will turn out to be a positive number. And that is the heart of the second law of thermodynamics, that the delta S of all the things involved has to either be 0 or positive. It can never be a negative number. Okay, so here's another example. One container is at 270, one is at 260. Again, you do the change in entropy of the one, the change in entropy of the other. You get the net change in entropy, and you'll see it is a positive number. The universe increased in entropy. If we were to imagine energy flowing from the cold to the hot, we would think that's not going to happen. But why not? It does not violate the law of conservation of energy. If we have 100 kilojoules leave here and the same 100 kilojoules appear here, that will still conform to the idea of conservation of energy. We didn't create or lose it, we just transferred it from one object to another. However, when we look at it in terms of entropy, we would notice that we would get a net change in entropy that's negative. And that is a violation of the second law of thermodynamics, because it's saying that we ended up with a macroscopic result that has fewer microscopic states than we started with. And that is not going to happen. Okay, when we look at it from a standpoint of pure statistics, you're always going to move from fewer microscopic states to more microscopic states. So heat can never flow from cold to hot. It violates the second law of thermodynamics. Okay, back in the early 1800s, we had a French scientist who was able to, even though this predates Boltzmann's ideas on entropy, to realize that we're going to have a system where we want to maximize how much of this heat is going to turn into work. And he is going to stumble upon, through lots of experimentation, what he believed, and it turns out he was right, the most efficient cycle for this engine could possibly be. And it looks something like this. Again, he did not have all the formulas for entropy that we have today, but it turns out that when an engine goes through this cycle, and we look at the change in entropy when heat enters, and the change in entropy when the heat leaves, that we get a net change in entropy of 0. And that is the best we could ever hope for. Most times the change in entropy is going to be positive, meaning we move to a more chaotic state, a state in which we had more microscopic possibilities of arriving at that state. But if we move our engine through this exact process, it will be perfectly efficient for these temperatures, based on the idea that we can never have a delta S that's negative. The best we can hope for is 0. It turns out that when we calculate that efficiency, it's going to follow this equation. Okay, so if we wanted to figure out how much work we could get out, best possible scenario, what we do is we look at how much heat left our hot source, that is, how much heat did we produce. We then figure out the change in entropy that occurs for this part of the engine. We say the best we can hope for is a net entropy change of 0. So then we're going to have a positive entropy change that equals our negative entropy change. So we take that 605, we use our new temperature, and we find our heat. Once we have this, we can work out how much how much work is going to come out of our system. And it would be 230. We can then find our efficiency using our W over QH, and we see that for this configuration, we would get an efficiency of about 39%. If we were to make the cold reservoir even colder, and we do the exact same work, we can see that we get much more of our energy coming out. So one of the big contributions of Carnot is that when we have a bigger difference in temperature, we can get a more efficient engine. Okay, here we raised the efficiency of our engine to about 94%. Simply by having a bigger difference between the hot and the cold areas of our engine.